Hello, everyone. My name is Rachel Skipper. I am just here to kick off today's session as I am in admissions at Syracuse, and you will have heard from me by now, or will be hearing from me in the future about your process of applying to Syracuse. I'm glad you are here to learn more about our physics department and sit in on a physics course with us. And we are certainly happy to have you here. We were just discussing how much we like to see physics majors coming into the university, and I see quite a few in the room here as well. For those of you who are interested in other topics, I suppose it's relevant for me to mention, you can also double major in physics alongside what you're considering. It would likely be a very useful pairing no matter what you're studying, especially within STEM. So please do keep that in mind during today's lecture. With that, I would like to kick it over to our faculty members, Professor Jenny Ross and Professor Eric Coughlin, who are here to chat with you about physics and have prepared a special lecture just for you. So with that, I will leave it to our faculty members and students. Please do ask them questions throughout the presentation and during Q&A at the end to engage with them. This is a really valuable learning experience for all of you, and we want to see you participating as much as you'd like to. So with that, thanks for being here, professors, and I will leave it to you.
Awesome. Thanks, Rachel. I'm going to just get started, and then I'm actually going to hand it over to Eric, who's going to run most of this lecture. You can think of me as his backup dancer for tonight. And but I just wanted to say hi. I'm the chair of the physics department. Actually, if you have questions about the department or anything about it, you can always just send me an email directly. Also want to talk a little bit about how we have classes in physics. So we often like to do more engaged learning, more active learning. Obviously, we're in person. So we'll tend to do a flipped classroom or a very short lecture with a lot of Q&A in it to get you engaged and interacting with the material during the class. And we also like to have you do a lot of practice. So you can do practice both by doing homework, which will actually leave you with some homework. If you're excited about doing it, you can certainly do it. But in addition, we do actually a lot of work in the class. We actually do real physics in the class. So I'm going to kick it over to Eric. He's going to give you a really good example of how we do this with a really cool topic. I'm super glad that you all came. Special relativity is super awesome. So without further ado, this is Professor Eric Coughlin.
Thanks a lot, Jenny. Can everyone hear me okay? Okay, thank you. Can everybody see this writing? Yes. So yeah, thank you, Jenny, for that introduction. My name is Eric. I'm an assistant professor here in the department. It's very orange. In the physics department, I haven't been here for very long, only about a year. I haven't been teaching for that long, but it's something that I really enjoy. And so today I'm just going to lead a little bit of a discussion about weird or funky physics near the speed of light, and as a consequence of what we call special relativity. But just to sort of give you some background and some sort of ideas, so the field of research that I'm in and what I like to do is actually in astrophysics and astronomy. And one of the things that I like to study quite a lot are explosions in the night sky, things that go boom in the night. And so when something astrophysical explodes and blows up, the stuff that blows up with it tends to move pretty fast. So how fast does it move? And the answer is near the speed of light, so substantial fractions of the speed of light. So the speed of light is a fundamental constant of nature, some of which you may have already encountered in your physics classes in high school. So the speed of light we usually denote with a lowercase c, and it's got this very well measured value, 2.99792458 times 10 to the 8 meters per second. So meters per second being the SI unit that we tend to use in physics. But if you're being lazy and you don't feel like carrying around all those decimal places, it's a pretty good approximation to just say that c, the speed of light, is about 3 times 10 to the 8 meters per second. So that's really, really fast, a lot faster than you probably can conceptualize. And so to give you an idea of how fast that actually is, if you were able to travel at the speed of light, you could go from New York to California in about 0.01 seconds. That's right, celerity has nothing to do with celery. So 0.01 seconds going from New York to California beats the crap out of the airlines. Nonetheless, it's probably going to be a while until human beings can travel that fast, but it's pretty interesting to think about. So what sort of things explode in the night sky? So some of the best known examples that have actually been documented since antiquity are what are known as supernovae. So supernovae are explosions of massive stars very near the ends of their lives. So at the center of a star, you have what is essentially a giant thermonuclear reactor, where light elements are being constantly what are known as fused into heavier elements. So the center of our sun, for example, is generating or is taking hydrogen atoms and fusing them together to form helium. And that generates energy, and that actually withstands the gravitational pull that the star has against itself. And so basically a star is just a giant balancing act through its entire life. But eventually the star runs out of fuel. Gravity starts to win. The star collapses in under its own gravity. And through processes that are not still entirely well understood, the star can actually reverse that infall, sort of bounce and throw off a bunch of material out into space in the form of what we call a supernova. And so typical energies involved in supernova explosions are 10 to the 44 joules, which is a huge number. The amount of mass that gets thrown off is about the size of the sun. The sun is 2 times 10 to the 30 kilograms. This is kind of par for the course in astronomy. You throw around huge numbers and eventually you just kind of get used to it. And so what you might have already heard in one of your physics classes is that energy is related to the kinetic energy of something via 1/2 mv squared, right? So E equals 1/2 mv squared. This is your kinetic energy. And so if we use E equals 10 to the 44, m is 2 times 10 to the 30 kilograms, and we take the square root, the velocity that we end up getting here is about 1% the speed of light. So these images here were taken by real spacecrafts, real telescope satellites that are showing kind of the aftermath of one of these supernova explosions. 3 here are just really well-known examples. Tycho's super remnant is the one on the left, and then the Crab Nebula is the one on the right. And honestly, I don't remember the one on the right. Crab Nebula is the one in the middle. Okay. So a second example, something that moves really fast, is what's known as a compact object merger. So you have 2 neutron stars, which is an object that has the mass of the sun, but a radius of about 10 kilometers. So really, really compact. These 2 objects spiral around one another and eventually start to merge and emit energy through what's known as gravitational waves. And so those are those kind of ripples that you see coming out from the center of this source. As they spiral together, eventually they touch, they coalesce, and they release a ton of energy in the form of what's known as a kilonova. So those 2 objects, the 2 neutron stars, at the time that they merge together, are actually moving at tens of percent speed of light, right before they come together and slam together and generate this explosion. So I did not make that movie. Credit there goes to the ESO, but it's really cool. And so we have people in this department that study gravitational waves and do some pretty amazing physics with these sources that we're observing all the time now, actually. Okay, third example is what's known as a galactic jet or an astrophysical jet. A jet you can sort of think of as a giant fire hose of plasma and gas that gets launched out from very, very close to what's known as a supermassive black hole. So supermassive black holes are objects with millions to billions of times the mass of the sun that reside in the nuclei or the very centers of galaxies. So at the center of our Milky Way, we have a supermassive black hole with a mass of 4 times 10 to the 6 or 4 million times the mass of the sun. The image that I'm showing you here is kind of a direct image of a supermassive black hole in a nearby galaxy called M87. So gravitons, not so much, or at least not so much in the department here, or at least not so much on the gravitational wave side. So we have people who are very interested in those ripples of space-time that were coming out, is the question I'm trying to answer in the chat. So these supermassive black holes sit in the centers of galaxies, and you sort of think of supermassive black holes as these kind of cosmic vacuum cleaners that eat everything that comes in their path. But what's really kind of surprising is that in some cases, these supermassive black holes can launch out material from very near their vicinity. So material is not coming from inside the supermassive black hole, but from very close to it. And so down here, this is an image in the radio showing this jet. It's this long straight feature here that's being launched out from the center of this galaxy, M87. So this expression here, is that the question? right? So this is saying the velocity of these jets, the velocity of this material v, is something like 90 to 99% the speed of light. So this material from the center of this galaxy is getting thrown out at 90 to 99% the speed of light. These giant like galactic fire hoses, and these things extend out over entire galaxies worth of space in the universe. And then finally, some of the craziest, weirdest objects in the universe are known as gamma ray bursts. These are really enigmatic things that were discovered back in the 60s that are these sudden bursts of gamma rays. So you're probably familiar with UV radiation from the sun. That's really harmful. If you ever had an X-ray done, X-rays are even higher energy than UV, but it's still light. And gamma rays are even higher energy still. So they're even higher energy than X-rays and extremely harmful if you come into contact with a lot of them at once. Luckily, gamma ray bursts come from very far away. And we think that gamma ray bursts are the result of the deaths of very rapidly rotating and very massive stars. But honestly, it's still a bit of an open question. I think people have mostly converged on this, but it's something that people are still thinking about. And what we've inferred about gamma ray bursts is that the material comprising the burst of radiation, or the material that gives off the burst of radiation, is moving at something like 99 to 99.999% the speed of light. Yes, and yes. But you're getting ahead of me, so just wait a minute. Okay, so what I'm just trying to give you are just some examples of things in space that move really, really fast. And so that's what we tend to do as astronomers. We tend to measure velocities in units of the speed of light. But what's so special about c, right? Why do we measure things in units of the speed of light? Why don't we just use whatever other speed we want? And the reason, there are actually three postulates and principles that are related to the speed of light that Einstein actually formulated back in the early 1900s. One of them is that nothing moves faster, nothing with mass moves faster than the speed of light. So it's sort of like this universal speed limit. And so unlike the speed limit on the highway, where you might push it 5 to 10 miles an hour over, nothing in the universe goes faster than the speed of light. There are some particles that people have hypothesized and theorized about that could move faster than the speed of light, called axions. I saw somebody mention that in the chat, but I'm talking about ordinary matter here with mass. So nothing moves faster than the speed of light, which is pretty interesting and weird. Second thing that's very, very strange is that every single observer actually agrees that the speed of light has the same value. And this is actually really strange when you stop to think about it, because you can imagine a scenario in which, say, I throw a baseball at 50 miles an hour, if I'm really trying. And if I'm, for some reason, moving relative to you at, say, 10 miles an hour, then your intuition tells you that you should probably see the baseball moving at 60 miles an hour, right? If I throw the baseball in the same direction that I'm moving, you just want to add my velocity to the velocity of the baseball to get the resultant speed. So to take like another example, you can imagine, say, that I'm in a plane moving through the sky. I have some pretty high speed, something like 500 miles an hour. And on that plane, there's a snake. And let's say the snake lunges at me at 10 miles an hour, right? And so again, your sort of intuition tells you, well, the speed of the snake relative to you on the ground should be about whatever the velocity of the plane is, 500 miles an hour, added to whatever the velocity of the snake is. Let's say it lunges at me at 10 miles an hour. And it turns out that that's actually just not the case when something is moving very, very close to the speed of light. So the speed of light is the speed of light, no matter who you ask. So if this snake had a laser beam attached to its head, right? So the plane is moving at 500 miles an hour. The snake is lunging at me at 10 miles an hour. I'm running away from the snake as fast as I can. None of that actually matters, right? The laser beam is coming out at the speed of light relative to me and relative to you, even though you and I are moving very fast with respect to one another. Okay, so it's a really bizarre feature of the speed of light that nonetheless is true. And then finally, the third thing that's sort of related to the speed of light is what's called the principle of relativity. that says essentially that there's no such thing as absolute motion. There's only relative motion, and every observer is equivalent to another one. And so again, to sort of take an example of how this works, let's say you and I are driving down the highway. I'm going 60 miles an hour northbound. You're going 60 miles an hour southbound, relative to someone who's just standing on the side of the highway for some reason. But I'm actually equally justified in saying that I'm actually just stationary and you're moving at 120 miles an hour southbound. Or you could also be justified in saying that you're stationary and I'm moving at 120 miles an hour northbound. And so all of those relative velocities are actually consistent with one another. There's nothing wrong with that. It's just that we each have a different interpretation of what's going on, and we're all equally justified in our claim of who's moving relative to whom. So it's only relative velocity that matters. Okay, and so today, what I want to do is sort of talk about this a little bit. Before I do, I'll just mention that there's some evidence, good theoretical evidence for this in the form of what are called Maxwell's equations. So if you plan on doing physics, eventually you'll encounter these in your career. Maxwell's equations describe the behavior of electric and magnetic phenomena. And one of the consequences of them is that there exist oscillating electric and magnetic fields that move at a very well-defined or well-posed speed. And so we know today that that speed is the speed of light, and that one way you can think about light is that it's an oscillating electric and magnetic field. But at the time, that was a really strange thing, because the prevailing wisdom, which most people would have agreed with then, is that if you're talking about a speed, you have to be measuring that speed with respect to something. And so for a long time, after Maxwell had devised or derived his equations, people were talking about something known as the luminiferous ether, which is kind of this pervasive medium through which it was thought that light had to propagate. And then Einstein came along around 1905 and said, no, that's all garbage. It turns out the speed of light is just a fundamental constant of nature, and everybody agrees on it. So there's actually good theoretical evidence to support these sorts of ideas. And so postulate 2, in particular, the constancy of the speed of light, has some really weird and strange implications for the way that the universe has to behave if that's actually true, if the speed of light is independent of the observer. One of them is called time dilation, which essentially means that time is actually a relative quantity and can slow down for moving observers. And so there's no such thing as absolute time anymore. Time becomes relative. The second thing is also extremely strange. There's this thing called the relativity of simultaneity, which means that if you measure two events as being simultaneous or occurring at the same time, if I'm moving relative to you, I might actually disagree with that statement and say that those two things actually occurred at different times, which doesn't seem to make sense, but it's actually a consequence of the same value of c being measured for everyone. And then finally, third very strange thing is space contraction. So lengths or distances between objects can actually change and contract if you start moving. And so space and time actually both start to become relative quantities. And things like the distances between objects and the time lengths, the lengths of time between things, actually change and depend on who you ask. So all these things are really weird. It'd be a pretty tall order to talk about all of these in a single lecture. And so today what I want to focus on is this thing we call time dilation. And what I want to show you is that we can actually derive a really cool expression for how this works in terms of the speed of light and the velocity of how fast something is moving. But before we get there, I want to give you a disclaimer. So as Jenny mentioned, in the physics department, we're really big fans of active learning and trying to get you engaged in the classroom. And so one thing I want to do throughout our discussion is ask you some questions. And there are 3 things that you'll need to know in order to answer them. One is just pretty much a definition, and I just want to tell you what it is. It's a light year. This is the distance that light travels in 1 year. Okay, 1 year being the time it takes for the Earth to go around the sun. So remember, the speed of light is about 3 times 10 to the 8. Right, so 3 times 10 to the 8 meters per second. 1 year is about 3 times 10 to the 7 seconds. So 1 light year is 3 times 10 to the 8 times 3 times 10 to the 7, which is something like 10 to the 16 meters. Okay, so that's a really big distance once again. But it's just a definition. It's just multiplying the speed of light times 1 year, and you get the distance that light travels in that time. The second thing I've written over my own drawing here is what's called a Pythagorean theorem. So this is something you probably learned in geometry. So if I have a right triangle, so two sides of a right triangle that meet at 90 degrees, the two sides, the two legs of that triangle are A and B. The Pythagorean theorem tells you that the hypotenuse of that triangle is related, the length of the hypotenuse is related to the length of the sides via this expression here, right? So a squared plus b squared equals f squared. Normally, people would call the hypotenuse c, so a squared plus b squared equals c squared, but I didn't want to call it c for pretty obvious reasons. So the hypotenuse in this expression is called f, okay? And this holds for any right triangle. And then finally, if an object is moving at some speed, call it v, it'll cover some distance x if it's moving for some time t, where x is just v times t. So if you're moving down the highway at 50 miles an hour and you travel for 1 hour, you cover 50 miles, right? So again, or if I have a rocket ship moving at some speed v for some amount of time, the distance it covers is just v times t. No, it doesn't matter what variable you use for the hypotenuse. Okay, so these are just the three things that I'm going to kind of rely on and use to derive what I think is a really cool expression that tells you something about time dilation. And I just want to give you sort of an example of how these questions work. So if we were in the classroom, one thing that I really liked to do is hand out, instead of doing clickers, which a lot of people tend to use, I use something that's less sophisticated, which is just a card that has the 4 letters A, B, C, and D, in which you can fold such that you only hold 1 letter up at a time. And so normally, you know, at the very beginning of the class, the very beginning of the semester, I'll hand out 1 per student, and I'll show a question like this. And what I'll do is I'll give you, say, 30 seconds to read the question yourself, so I won't read it for you, internalize it and think about it and come up with what you think is the answer to the question. But I don't want you to all answer at different times, right? So don't answer when you think you know the answer. I want you to wait. And so I'll give you something like 30 seconds. And after that 30 seconds go by, I'll say, does anyone need more time? If no one answers me, no one says, yes, I need more time, I'll say, okay, let's vote. 1, 2, 3, vote, right? And I want you to show your answer, okay? And so if we were in the classroom, you would just show your answer in front of you, so that only really I could see it, so that not necessarily your friends or your neighbors could see what you're voting. So then if not enough of you get the right answer, I would say, okay, why don't you turn to your neighbor and discuss what you think the right answer is and why you chose what you did. And then once you're given enough time to do that, we would have a revote, and hopefully a greater percentage of the class would get the right answer. So we don't really have that much flexibility being online. And so what we're really going to do is just the first half of that. So what I'll do is I'll put up a question like this. I'll give you 20, maybe 30 seconds, ask if you need more time, and then say, let's vote. And then on 3, if you wouldn't mind, put your answer, the answer that you think it is, in the chat. Okay, so let's give this a shot. Please read this question and place your answer in the text box after I say to vote. So don't do it right away. So go ahead. Okay, let's have a vote on 3. 1, 2, 3. Yeah, very good. Thank you. That was great. Right,
yeah,
exactly.
That worked really well.
Yeah. That was much better than I was expecting, I won't lie. Yeah, exactly. Thank you all. So this is just an application of that last expression that I said I wanted you to know, right? So x, whoops. So x, come on. X equals v times t. So v is 0.5 times c. T equals 4 years. C times a year, that's equal to 1 light year. And 4 times 0.5 is 2, right? So 2 light years. And a lot of you answered that. So really great job. Thank you. That was awesome. Okay, so this is what we're going to do. I just have a few slides that kind of go over a derivation of something that's really cool. It's this expression for time dilation. Okay, so let's give it a shot. So the way that we're going to do this, whoops, I didn't want to do that. So the way that we're going to do this is through what's known as a thought experiment. So we're not actually going to go into the lab and conduct an experiment, which is something that I would never trust myself to do anyway. Instead, we're actually going to sort of abstract ourselves and think about how a situation must work according to nature if it's really true that the speed of light is the same for everyone. And in the process, we're going to derive something called this expression for time dilation that relates the passage of time from one person relative to another. Okay. Okay, so to start off this experiment, let's imagine that we have a person sitting alone in a room, and the room has some width d. Okay, it can be whatever you want, 10 feet, 15 feet, 20 feet. At the other side of this room, immediately opposite of this person, you have a mirror. And what this person does is shine a laser beam across this room such that it traverses the room, hits the mirror, and comes back. Okay. So how much time does it take for the light ray to actually achieve this? And so you remember from that expression that we just used in the previous example, in the previous question, the distance that something travels, if it's traveling at some speed v over some time t, is equal to the distance, right? So 2d is the distance that the light ray travels. It's traveling at speed c, and it'll travel that distance in some time, which I'm going to call delta t prime. And so if I rearrange this little expression and solve for delta t prime, that's what I get. Okay. So delta t prime is the time measured by someone standing in this room for the light to cross the room and come back. Okay. And remember, the speed of light is this fundamental constant that everybody agrees upon is the same thing. Okay. Same value. Okay. So I don't think that's too surprising. So now let's change it a little bit. Let's imagine that instead of being in some room, some stationary room somewhere, this person is actually traveling in a train, and this room is actually the car of a train that's moving at some speed to the right. According to me, I'm standing on the ground watching this train go by. For historical reasons, I think like in the early 1900s, it was the dominant mode of travel to be moving around by train. And so a lot of these thought experiments, if you like read about them, they always involve trains. So I figured might as well stick with it. Okay, so let's imagine that this person is now moving at some speed v, going to the right. So c equals 2.99792458 times 10 to the 8 meters per second, or 3 times 10 to the 8 meters per second. Okay, so let's imagine now that this person is moving to the right at some speed v. Okay, so how do I interpret how this whole process works? Okay, so some amount of time goes by. The person in the train, traveling in the train, moves to the right at her speed. And at the same time, she starts to shine this laser beam such that it can traverse the car. Okay, but this laser beam is staying in front of her the whole time. And so instead of just going straight up and down, according to me, I actually see it follow this diagonal path. Okay, this is what the light ray does in the lab, quote unquote, right? According to me, who's just standing stationary with respect to the moving train. Okay, and remember the person before who's stationary with respect to the mirror just sees it go straight up. I, watching the train go to the right, actually see it make this diagonal path. Okay, so some more time goes by, and eventually the light ray returns, and it makes its return trip, and it comes back to the place that it started. Okay, so this is the same event, the same thing that's happening. It's just now relative to someone such that the train car or the laser beam moving is actually moving along at some speed, some different speed. Okay, so now remember that the speed of light is the same for everyone. So this light ray makes the trip, right? So it goes up and back in some amount of time, delta t. Okay, so that means that it covers half the distance. So namely, this distance right here, this distance must therefore be c times delta t divided by 2. okay? If delta t is the total amount of time it takes for the light ray to go up and back, then in half that time, the light ray covers half of that distance, okay? So this line here, this kind of diagonal line here, this distance here, call it x, is equal to c times delta t over 2, okay? And you can think about it like the whole thing here, up and all the way back, is the total distance that the thing travels, that the light ray travels. That total distance is c times delta t, which is delta t is the amount of time it takes, according to me, for the light ray to go up and back. And so half that distance is just equal to this diagonal line here, and that's c times delta t over 2. Okay, this vertical line that I'm drawing down here is the same, right? Remember we called that d, that was just the distance of the train car. And then similarly, right, the train car is moving to the right. It will travel a total distance, so this distance here, v times delta t. And so it covers half of that distance in delta t over 2. Okay, and so this distance right here is v times delta t over 2. This distance right here is c times delta t over 2. And then this distance, this vertical distance here, is the same d. Okay, and now your intuition is going to say, wait a minute, this can't possibly be right, because the speed of the light ray has to change, right? I mean, once again, right, you just take this silly baseball example, right? If I throw the baseball forward in front of me, if you're now moving, if the whole train is moving, the baseball's got to be moving with the same, right? You got to add that velocity into it. But that's actually not true. And it's what's really, really strange is that according to both of us, the speed of light is exactly the same. It's still the same c, even though we're moving with respect to one another. Okay. So what we've done is we've constructed this set, a couple right triangles here. Okay. And remember, so delta t is the amount of time it takes, according to me, for the laser beam to cross the train car, right? It goes up here, it hits the mirror, right? Here's our mirror. And then it comes back down the other side and returns to this person. Delta t is the amount of time it takes, according to me, for that whole process to happen. And I'm sitting watching the train car go by. So remember, right, we talked about our Pythagorean theorem. Here are the two sides of my triangle. Here's the hypotenuse, right? So this is from our previous thing. This is A, this is B, and this is F. Okay, and so this is just the Pythagorean theorem. Okay, so nothing too crazy yet, I don't think. But let's remember what we said for the person who's moving with the car, right? The person for whom the mirror is stationary. They say that the amount of time it takes for the light ray to go up and come back, remember we call that delta t prime, that's just 2 times d divided by c, right? Or said another way, 2d equals c times delta t prime. And so remember, the way to think about this, delta t prime is the amount of time measured by someone moving with the car for this light ray to go up and come back. In the amount of time it goes up and comes back, it traverses this distance twice the width of the train car. And the whole time it's moving at the speed c. So what we can now do is actually plug this expression into here. Okay, we can cancel the factors of 4. That goes away when we take the square. What we can now do is rearrange this expression and solve for, sorry, I'm like running off of my page here. Sorry if that's really messy. But the idea is that we can sort of just rearrange this expression and we can solve for this quantity delta t in terms of delta t prime. Okay. And so I might have went a little quickly there, and I'm sorry if I maybe lost you a little bit, but the algebra is not really the important part. The important part here is what we've derived, and what we've apparently shown is something really that seems like it can't possibly make any sense, right? Because what this tells you is that the amount of time that it takes, according to you, moving along with this train car, right? Remember, that's called delta t prime. That's this quantity right here. That time is actually not the same as the time that I measure when this train car is moving relative to me. I measure this quantity right here. This is actually 1 over the square root of 1 minus v squared over c squared. That's always greater than 1. And so it actually takes longer, according to me, for this light ray to go up the train car and come back as compared to how long it takes according to you. Okay, and this expression, this delta t related to delta t prime, is a really famous expression, and it actually gets used all the time in astronomy. It's called this time dilation expression. And this quantity here, this 1 minus v squared over c squared to the minus 1/2, people call this the time dilation factor, or it's also known as the Lorentz factor. Okay, and remember, v is the velocity of the train car relative to me standing on the Earth. And so another way of saying this is that time is sort of dilated relative to a stationary observer. Things take longer, according to me, compared to how long they take according to you. So if something dilates, like your pupil dilates, it gets bigger, time gets longer, which is a really, really weird thing to conclude. But it turns out that it has to be this way if the speed of light is the same according to everyone. And this factor, this gamma thing, for normal speeds is extremely close to 1. And it's actually why you haven't noticed this effect already in your life. Because if we take something like the speed of an airplane, 500 miles an hour, let's say, that's 224-ish meters per second. That's much, much less than the speed of light. And if you calculate this thing we call the Lorentz factor, for that specific speed, it ends up being 1.0000000000002. Right? So that's 1 plus 2 times 10 to the minus 13. To give you an idea of how small that is, the size of an atom is like 10 to the minus 12-ish, which is close enough to 10 to the minus 13. So 10 to the minus 1 part in 10 to the 13 is about the ratio of the size of an atom to the size of me, my height, right? So really, really small. So even moving it with the speed of an airplane, you don't measure this effect at all, right? But this is a relativistic effect. So it starts to matter when things start to move close to the speed of light. And so if you plot this, so this is this quantity. So this is this quantity gamma. You can plot it as a function of v over c. And you can see that down here, okay, v over c is much, much less than 1. And this gamma, this factor that relates the amount of time it takes for things to happen relative to you versus me, is very, very close to 1, which means that the amount of time it takes for these things to happen is basically the same according to you and me, and we would never be able to know the difference. But as you start to get close to the speed of light, this actually becomes of the order 2, 4, and then all the way up at 10 when you get really, really close to the speed of light. And so if you say, let's take an example, delta t prime, the amount of time it takes for something to happen according to you is 1 second. If you're moving at 50% the speed of light, that actually takes 1.15 seconds according to me, if your train car is moving at half the speed of light. Okay, so that's not too crazy. If you're at 90% the speed of light, it actually takes a little more than twice as long. If you're moving at 99% the speed of light, it actually takes 7 seconds. And at 99.9% the speed of light, it takes a full 22 seconds in order for that light ray to cross the train car and come back. If it takes 1 second according to you, which is really bizarre. Okay, and so this is like a really fundamental and very cool expression that we just derived by using nothing more than geometry, pretty much. And that's one of the really cool things about physics. And I think it's one of the things that in the department we really try to emphasize is that these concepts, it's the conceptual sort of understanding is that what really underlies physics. And oftentimes, you can get lost in some of the math, but in this case, the math is actually really is stuff that you have all seen before. And you can use that to derive really, really cool expressions about the way that the universe works and in ways that are not at all obvious. Okay, but there's something that's even cooler about this, because if you look at this expression, there's actually nothing in it that depends on laser beams or the width of the train car or anything like that. And so in other words, we can make the width of the train car arbitrarily large or small, and this same expression holds. And so what that implies is that this expression that relates time intervals as measured by me, right? Remember, this is my time and your time, where you are moving with the mirror that's watching the laser beam go up and come back. this expression must just be valid in general. And what that means is that intervals of time are actually longer according to me than they are according to you, which is really, really strange. So let's do an example that tries to use some of this formalism that we just developed to see this kind of in action.
Eric, can you put up the Lorentzian equation again?
Yes, sorry. Thank you, Jenny. Okay, why don't we have a vote on 3? 1, 2, 3. Okay, I'm getting a handful of B's and D's, which is okay. Okay, so let's kind of deconstruct this problem and see what's going on here. So I say you're traveling along with a relativistic jet. You're moving at 3/5 the speed of light, 60% the speed of light relative to me. And as you're riding along your relativistic jet, you start boiling a pot of water because you want a cup of tea. Okay, so relative to you, stationary with respect to the tea kettle, it takes 4 minutes to boil the water. Okay, so what does that mean in terms of this expression? Okay, so that means that delta t prime is equal to 4 minutes. Because remember, delta t prime is the amount of time it takes relative to someone that's moving along with whatever's happening. Delta t is the time that I measure if I'm watching you move by at 60% the speed of light. So I tell you that v over c is equal to 3/5. And so v squared over c squared is 9/25. 1 minus 9/25 is 16/25. And the square root of that is 4/5. Okay. So delta t is equal to 1 over 4/5 times delta t prime, which is 5/4 times delta t prime. Okay. So once again, this is the amount of time it takes according to me. So I'm watching you move by me, boiling this pot of water. According to you, it takes 4 minutes. So 5/4 times 4 minutes is 5 minutes, which is crazy, right? Like, how can it possibly take longer to boil a pot of water if I'm just watching it move by me, right? So let's do another one. Oops. Yes, sorry. The time dilation expression. I'm actually not sure if there's like a formal name for it or not. This thing is definitely called the Lorentz factor. It's after Hendrik Lorentz, who was a mathematician in the early 1900s who actually came up with this expression before Einstein did, but didn't actually understand the implications of it, as far as I'm aware. Okay, does anyone need more time? I think I didn't hear anybody. So let's have a vote on 3. 1, 2, 3. Yeah, very good. Right, B. Okay, so this is actually the third principle that we talked about, right? This principle of relativity. Because while I see you moving to the right at 60% the speed of light, you're equally justified in seeing me moving to the left at 60% the speed of light. So if I now start boiling a pot of water, I measure that it takes 4 minutes. I'm moving at 60% the speed of light relative to you. And by the same math that we just did in the previous problem, we don't have to do it again. We know that it's going to take 5 minutes according to you, which is like bizarre, right? And so what that means is that questions like how long does it take to boil a pot of water actually don't mean anything anymore unless you say relative to whom, right? You have to say relative to the person that's standing next to the pot of water, right? So the pot of water is not moving off at 90% the speed of light, right? That's the person for whom things take 4 minutes. Okay, so there's no such thing as absolute time anymore. We've just deconstructed that idea. Sorry. Okay, I'm almost done. Okay, so everything takes longer relative to a stationary observer. Okay, if I'm watching you move by, more time runs on my clock than it does on yours. Okay, so let's take another example. So how do we age? Okay, this is something you become painfully aware of, literally. So how do we age? Your cells start to break down. In a physicsy speak way of saying this, you're a very ordered person. It took a lot of work to put you together. And as you age and as time goes on, the universe is just kind of continuously breaking down your order into disorder. We're generating entropy. And something like, looking at a stationary object, right? So the thing is that the moving observer part, I'm always equally as justified as saying that the other thing is doing the moving, is what I was trying to say before, this sort of relativity concept. So moving pots of water boil more slowly, according to me, who's watching it. So something like a wrinkle will form on your face on a time scale of something like 40 years as your skin just degrades and you get older and gravity keeps trying to pull you down. Okay, but as we just said, right, 40 years doesn't actually mean anything anymore, right? So wrinkles form on your face relative to whom? Well, I mean, you're moving with your face all the time, right? And so when we say 40 years, it really means relative to the person who's moving along with you, who at any given time could be any number of people, but throughout your life, it's also you. Okay, which is a really convoluted way of saying your face ages according to you, right? So it takes 40 years relative to you, for whom your face is stationary, to form a wrinkle, okay? So let's do one more example. Okay, let's have a vote on 3. 1, 2, 3. Yeah, very good, right? So it's the same sort of expression that we used before. V over C is 3/5. You do that algebra. And what you come up with is that while it takes 40 years for a wrinkle to form on your face according to you, 50 years passes according to me, which means that you actually age more slowly relative to me, right? If you're moving at 60% the speed of light, 40 years goes past, 40 years goes past according to you, whereas 50 years has gone past according to me. And this sort of effect becomes even more pronounced as you get closer and closer to the speed of light, right? This effect becomes more noticeable. Yeah, we just need to get, that's right, yeah. We need to get spaceships that travel close to the speed of light. So there's a really cool problem in special relativity that's also said to be a paradox. It's called the twin paradox, that explores one of the very strange consequences of this relative aging thing that's really strange. And so normally, I don't know, I've actually taken a lot of time. So normally I would hope to have enough time to sort of give this out. Yeah, this is related to the twin paradox. So what we would want to do, so I just posted a link in the chat. If you go there, hopefully it takes you to this document that I came up with that just explores this relative aging thing in the context of a pretty well-known example known as the twin paradox. It basically has to do with a twin who travels out at some substantial fraction of the speed of light, turns around and comes back. Despite the fact, despite the fact that they started out their lives at exactly the same time, because of this relative motion and this relative aging stuff. Yeah, interstellar, exactly. Well, so interstellar is a little different because the guy's sitting near a supermassive black hole. And so that's actually gravitational time dilation, which is even weirder. And it's something that I would love to talk about, but we definitely don't have time. So, okay, so that kind of wraps it up. So this time dilation thing, moving objects age more slowly, which is bizarre, but it's the way the universe works, it turns out. As I said at the beginning, there's a couple of other really strange things that are consequences of special relativity and things moving near the speed of light. There are these things called Lorentz contractions and relativity of simultaneity that are super weird, and that I think, if this were an entire course, we would certainly get to with examples, sort of like I've already shown you here in the context of time dilation. But I've been talking for a while, and so I think let's just end it here and see if there are questions.
Thank you, Eric. That was awesome. I'm going to remove your spotlight so we can see everybody. If you want to turn on your cameras, you can switch the view to the gallery so you can see each other or whatever. If you want to ask a question, go ahead and you can just unmute, or you can write it in the chat. Either one is fine. And it can be about physics, or it can be about other stuff too. Rachel's still with us too, and she can answer other questions about admissions if you have those. Do you want to do the time machine one, Eric? So Aaron asked, if I were to invent a time machine, would I need time dilation?
You need time dilation. I guess it depends on how your hypothetical time machine works. Honestly, I'm not really sure. I mean, the context of time travel in astrophysics usually involves black holes and these things called closed time-like loops that exist inside event horizons. It's stuff that gets pretty, I wouldn't call it skeptical, sort of hypothetical because it's all inside black holes. So I'm sure that something like time dilation occurs, but honestly, I'm not familiar enough with the detailed math of this to really give a confident answer. But probably, I would think your time machine would have to invoke time dilation in some way.
Okay, so Jeremiah asked, what kind of careers are available in the astrophysics world in terms of employment?
Sure. So, I mean, a lot of people, so myself included, go into academia. And so like a traditional sort of path is to go to undergrad. You finish your 4-year degree, you go to grad school, which can take, 5, 6, perhaps even 7 years. And so I did my PhD at Colorado. You go on to postdocs where you do research, and then eventually you try to land yourself in a professor tenure track position. But that's not the only thing that you have to do. In research, particularly in undergrad and in grad school, you're sort of demonstrating by getting a degree that you can think critically and you can solve problems. And that's valuable to a lot of people across many different fields. And so, I mean, I know people who have gone into what's known as industry. It's kind of like a weird kind of catch-all phrase, but I know people who are like working for Google, for example, doing programming type jobs and things that I'm probably not allowed to know about. But you can do a lot. Yeah, I mean, you have a lot of different options open to you. Yes.
Yeah, and I think in particular with astro, there's jobs at NASA. There's jobs in other industry. A lot of times people will start in one, and you will end up learning a lot of programming. You're learning a lot of image analysis, and in this world of big data, that's a lot. There's a lot of data out there of different kinds, but they use the same kind of techniques that you would use from astrophysics. So you are open to having kind of these big data, technology type of jobs. Even if you started with the data that you were looking at was astro data. So I think there's actually lots of stuff, like Eric said, people want critical thinkers. So
I know somebody who studies like vegetation, like the growth of like vegetation across continents, like over time, for like this little startup company in New Mexico, which sounds really cool. That's just one example.
Okay, next question says, what sort of courses do you all mainly teach? So Eric, what classes are you teaching?
So right now, I'm teaching 2 things. So we have an intro level electricity and magnetism course. So it's kind of our big introductory level E&M course. And so we talk about electrostatics and magnetostatics. And so the semester is just finishing up right now, but you kind of go through the first couple like main topics in electricity and magnetism, so electrostatics and magnetostatics. And then we also have independent study courses. And so I'm simultaneously teaching one of those with another professor in the department. His name is Duncan Brown. And so with a couple of graduate students, we're doing an independent study on topics in fluid dynamics in astrophysics.
And then next semester, what are you teaching?
Yeah, and so then next semester, I'm teaching a course called Stellar Astrophysics. And so it's sort of an introduction to the interiors of stars and how stars work, that sort of stuff. And so that is a 300 level course. And so it's sort of designed, we want to draw you in as a physics major. And so the hope is that it's a cool course. It's fun to learn about that sort of stuff.
And then this semester I'm teaching physics 1, which is your kind of standard Newton's. So not the Einstein part, but the Newton's mechanics part, F equals ma, that kind of stuff. But it's the one for physics majors, and we do use calculus. a lot of the students are in calculus at the same time. We're using the calculus that you're seeing in your calculus class, but we're using it in our physics class. And it's a really foundational course. It's a small course because we don't have a huge number of majors every year. So it's really personal. So as opposed to the one that Eric is teaching, the E&M course, that's actually the one that's geared towards the engineers. If you are a physics major, or if even you're just considering a physics major, we'd love for you to come and cohort with the other physics majors, and you're in a small class. The room only fits 21 students. So, and we interact, you know, I actually have a TA and I have a coach. So we do a lot of this same kind of stuff where we, you guys do problems in class and we walk around and help you one at a time. So you get a lot of personalized attention in our physics classes. All right, next question. Does Syracuse offer any astronomy options course-wise? Yes. Eric is teaching one. We have another course. We have actually 2 at the 300 level. We have 2 at the 100 level. And one of the things that I'm really excited that when Eric joined our department, is that we're actually working on creating an astronomy major. Right now, we don't have that major because we have to go to the state of New York and get it approved. So it takes a little bit of time. But we have enough courses where if you wanted to specialize and basically do an astronomy core track, you could do a physics major, either a BS or a BA, and you could kind of specialize and take more courses in astronomy than in other things. And we're actually looking to add more kind of upper level and more advanced courses, not like super advanced, but more like we need a more advanced laboratory that's more astronomy based, things like that. And so we will be putting that together over the next few years. If it's something you're really interested in, when you get here, again, there's not a ton of you, right? So we can kind of make sure that we're offering the classes regularly that you would want to see. So, and I have students who tell me, we had a student who was interested in nuclear physics. We had a nuclear physics class on the books, but we hadn't taught it for a few years. We offered it so that she could take it. So that's the kind of thing that we can do in the physics department, making sure that you're seeing the classes and seeing the material that you want. Would it be possible to double major or major minor in astronomy and physics? Yeah, so like I said, right now we don't officially have an astro major. So that would be kind of a physics major with an astronomy bend to it, but we're working on getting that astronomy major because, well, we're the only ones who can offer it. You can't get an astronomy major from geology. So you have to take physics with us. And so, like I said, it may not be official, like on your transcripts that it was astro, but anybody who will look at your transcripts will see the large number of astro classes that you've taken. And astronomy graduate programs or other like astronomy jobs, they really need you to have that physics background. So it's much easier to go from physics to astronomy than the other way around. If you just do an astronomy major, it's much harder. You're going to have to pick up the physics along the way.
I would definitely second that. So my undergraduate education was much more geared toward physics. And it was definitely, you have to kind of learn the lingo and the terminology when you go to grad school, if you go to grad school in astronomy, but it's definitely a lot easier to learn the lingo than it is to learn the physics that goes along with it.
Okay, so do we have concentrations within the physics major? So we are actually working on that. Again, we just want to make sure that we're offering enough of these kind of topical courses so that if you're interested in certain things, you can have that opportunity. And also, like I said, we're happy to alternate or change what we're teaching so that we're hitting what you're interested in. Right now, we're working on, like I said, astronomy. We also have a biophysics track, and we also have biophysics / medical physics, if that's something you're interested in. And we also have a new track in quantum information science, which actually does have a kind of a 300 level and a 500 level course. And so quantum computers is another big thing that we have here. And with that course in particular, there are internship opportunities. You could even do an internship during your junior year, and if you wanted to do that instead of study abroad. And you could go down the road to Rome Air Force Base, where they have this really amazing quantum computing center, or you can do the research on campus with us. So there's a lot of really cool opportunities in quantum computing too. So this one says, does Syracuse offer any virtual biology classes in terms of pre-dentistry? I'm going to let Rachel take that one.
That's niche. We do have a pre-health session that's recorded that I can send you. You can watch it on YouTube, where our pre-health advisors who work with pre-dentistry, pre-med, pre-health profession students, and they talk about what kind of options Syracuse offers, what kind of coaching they offer. We are not offering a biology classroom like this one for prospective students. I keep it to 3. This is your STEM option for this semester. I will, though, now that I know you're interested, keep that in mind for admitted student options, which will be next semester. But I left a comment in the chat. If anyone's wondering about classrooms and other majors besides physics like biology, email me. I'll put you in touch with a current student and you can ask them any questions you have about what their classrooms are like.
Great. The next question says, is it possible to be a theoretical and experimental physicist rather than just being one or the other? It depends on your subfield. So there are some subfields where the jargon and the way that you solve the problems is really diverged. But actually in my field, I am a biophysicist. I also study what we call soft condensed matter. That's basically soft materials like your skin or, this outfit, whatever. Almost everything in our world is soft materials. And that's a field where you can still be a theorist and an experimentalist at the same time. In fact, among my graduate students, I have 2 students who are jointly advised by a theorist, Professor Jen Schwartz and I. So they have advisors. They're both named Jenny. So that's confusing. But because she goes by Jen. Jen is a theorist. Jenny, me, is an experimentalist. These people will actually be learning both, and they will be able to do that. So there are certain subfields where basically, if there's a subfield where the theory isn't that well developed yet, then actually a lot of times people will be still able to do both. The more mature the theory is, the harder it is for you to do both of those things simultaneously. Okay. Yep. Did you want to add anything?
Yeah, I was going to say in astronomy, it's less experimentalist and more observer. And so astronomers, we tend to classify ourselves as either a theorist or an observer. And so I think like an observer is something you would kind of think about classically as an astronomer, like looking through a telescope. So I actually don't do that. I'm a theorist. And so I actually have never professionally looked through a telescope. And so the type of work that I do is more math and physics, actually, and trying to understand the observations as opposed to take the observations themselves. But we work together all the time. We have to. It's the way the field works.
Okay, so Owen has a cool question. What percentage of the speed of light are humans currently capable of traveling at?
Yeah, I did this calculation earlier because I was thinking about it. So the 500 miles an hour that I was saying before for like a plane, I think is like 1 part in a million. So it's like 10 to the minus 6 times the speed of light. We as human beings, we probably can't get up too much faster than that, I would say. So, maybe 1 part in 10 to the 5, 10 to the minus 5, the speed of light. So even then, right, go ahead.
Oh, I have a question. This is a thing that I always think about because I read a lot of sci-fi myself. And in the sci-fi books that I read, which are the Expanse series, they create artificial gravity by accelerating the ships, right? So basically the ships are like giant office buildings and they get accelerated. And so the people are being pushed to the floor. And they'll often accelerate at 1G. So it'll be just like you're on Earth, right? And I always think about like how long would they have to accelerate before they actually hit a substantial fraction of C? And it's a really long time. They'd run way out of fuel way before they could do it.
Interesting.
Yeah.
That's a cool calculation.
But cool. Yeah, I think, the thing is you don't feel the velocity. Once you're moving at that speed, you don't feel it once you're in an inertial frame, right? So it's not like it would hurt you to move close to the speed of light. You wouldn't even notice it, in fact. It's the acceleration that's hard, right? Remember, F equals ma, so it's A is where you get your force from. Okay, next question from Daniel. Wouldn't these principles also state that objects have kinetic energy even if they're stationary?
I don't think so. Right. I mean, the thing that's always coming into it is the velocity. So if something's not moving, right? Me and the pot of water who are sitting right next, the pot of water sitting right next to me, that has zero velocity according to me, so it doesn't have any kinetic energy. It has rest mass energy, which is another weird consequence of special relativity. That basically, by virtue of having mass, something has a lot of energy, and that's what people used. Like in experiments a long time ago related to the atomic bomb and stuff. But
that's the famous equation, right?
Yeah, E equals mc squared, exactly. Yeah. Yeah.
Okay, so the next question says, what kind of research opportunities are available at Syracuse University? Lots. So one of the things I really love about being at Syracuse University is that we are a research department. We're an R1 department. We have research grants. Every single faculty member is research active, and majority of the faculty will take undergraduates in their research groups. But like I said, there's not a ton of undergrads in our major, which means everybody can have the opportunity to do research if they want to. The research groups we have, like Eric does computational astrophysics. We have some high energy theory. We've got biophysics, soft condensed matter. There's quite a bit of that. We've got both theory and experiment on that one. We've got quantum information science, both theory and experiment. We've got gravitational waves. We've got people who work on neutrinos and people who work on quarks, really trying to understand what matter is made out of. And so anything else? Oh, and then one person who works on nuclear physics as well. So there's quite a bit of opportunities. And of course, anything that we're not doing here, we'd be happy to help sponsor you to get a summer research experience for undergraduates, which means you need letters, which we can write you letters of recommendation to get into one of those as well. Michael says, is it possible to double major in something like theoretical physics and engineering? Absolutely. The physics major is actually not super overloaded. You could finish the whole major in 3 years if you wanted to. And that's not like weird. We're not like, have not very much to do in physics. It's just, that's how physics is. In physics, we teach you classical mechanics, E&M, electricity and magnetism. We teach you stat mech, and we teach you quantum mechanics, and we do that twice at the undergrad level. So there's basically 8 courses. We've got lab courses that you have to take, and then you fill in with a bunch of kind of specialty courses. But it's not a huge like weighty thing. But each course is really, you're learning some really essential stuff. But it's not. It is totally possible to double major. We have a lot of double majors with computer science. We have double majors with math. It's very common. We have actually double majors with visual and performing arts. We have lots of double majors, actually. Next question. Does mass have any relationship to traveling at the speed of light? And if so, how does that affect the relationship between time and the speed of light? So what happens with mass when you're getting close to the speed of light? I think it gets harder to push.
Yeah, so I think it's your momentum goes up very, very fast as you get closer and closer to the speed of light. And so if you think about it as like moving increments closer and closer to the speed of light, exactly like Jenny said, it gets harder and harder to push you because there's this kind of relativistic inertia that increases as you get closer and closer to the speed of light. So light has no rest mass, and so that's why it's allowed to travel at exactly the speed of light. But anything with a finite mass can only get asymptotically close to the speed of light. And if you tried to hit the speed of light, it would take an infinite amount of energy to get you there because of the fact that you have mass. So it is intricately tied to moving close to the speed of light, I would say. In terms of time, I don't think so.
All right, Ian asks, do we have a study abroad program within physics? We do not, but there is one study abroad program, I believe. I want to say it's in Ireland or England, where we do accept the physics courses from that program. On the other hand, like I said, you can basically finish the physics degree in 3 years, which means taking up 1 semester for study abroad in your junior year will not derail your physics major at all. Totally reasonable. So what you could do so what we have is, like I told you, you take the first 4 classes and then you take the next 4 classes, and then you have other stuff that you have to do, labs and specialty courses. Those last 4 classes, they're the 500 level physics courses. 2 are offered every fall, 2 are offered every spring. So if you go abroad, instead you'll just won't take one of them and you'll have to double up in the next semester, in the next year. But totally reasonable, totally doable. I did it. You can do it. I know you can. It'll be, yeah, totally doable to go abroad. Next question. Ask Rachel to post the email for undergraduate admissions. And okay, she posted the email, follow links. Great. Okay. What is an example of what real biophysics works with? Real world examples. Well, hitting maybe too close to home, we actually have a group of people who are working on COVID right now in biophysics. The idea is that so what they study are the mechanics of the cells. So you think about your cells and you think about actually, if you were to smush a cell, right, a single cell, it would pop back. So one of our researchers, Allison Pattison, she actually studies the things that cause your cell to kind of be springy. And there's like stuffing inside. It's like when you get a box from Amazon and you got a bunch of stuffing inside, there's proteins inside that actually its job is to keep it springy. And there's ones inside your body that make sure that your nerve cells don't break every time you bend your arm and things like that. And what she's found actually is that when viruses come and attach to the surface, that the vimentin inside, the protein inside that makes it springy, actually can affect how easily the virus can get into the cell. So that's a really close to home example of what biophysics can do. We also have people who are studying mechanics of whole tissues. You can understand how robust, like plant cells are, which is important, right? You don't want to have fragile plants that just fall apart. And in particular for crops like corn and things like that. We have people who I studied things that are related to mitosis or cell division. That's really important because when it goes haywire, you get cancer. And when it works well, that's how you get development, or wound healing, right? All of these things are important. So there are a lot of real world things, and soft matter is another one. And we have, like, for instance, we have somebody who's studying materials, thin materials. And you think, well, that's weird. I mean, you see thin materials everywhere, right? So like your clothes are like a thin material, things like that. So what could it be good for? One of the things that they're doing is actually using thin materials to create inflatables that will help to rotate people in hospitals. It turns out when people are sick in a hospital, if they lay on their back all the time, they atrophy and their blood starts to pull in the back. And so you actually have to have people come and pick you up and rotate you around. And it would be much better if you and then that can hurt them too, because now you're having to pick them up and it's all awkward. And so instead, if you can use an inflatable to actually do this. And so it's basically like, did you ever see Big Hero 6 with like the big inflatable robot? That's basically what they're trying to figure out if that works. And they're using physics to do it. So these are real world applications, right? Real world things that we're all working on here at Syracuse University. Okay, Ian had a question about, what do you think about the James Webb Telescope? Can you tell me in regards to which thing, Ian? You want to unmute? Like, should it exist? Should it be named James Webb? Is it going to give us good pictures? I don't know exactly.
I mean, I think, the science of JWST is going to be really crazy because it's able to probe what's known as exoplanetary atmospheres. So planets and other solar systems and their atmospheres and the possibility of life. And at the same time, be able to understand the very first galaxies and stars that formed in the universe, which are sort of among the areas that people are still investigating very intensely, theoretically, to this day. And it'll also be able to tell us stuff about our own solar system. So I think JWST is multifaceted and is kind of amazing for one spacecraft to be able to do all of that. I don't know if that's what you were asking.
Let's see. Abigail asks, what other fields are there in space science? So in addition to what you can learn from in the physics department and the classes and research that we do here, There is also an aerospace, I believe, and program in engineering. I think that's right, but I'm not sure because I'm not in not in that group. We do have students who tend to double major or they take a few classes over there. Like I said, we can be flexible, so we can offer physics credits for other courses. Basically, you could take some classes over there, but we would give you credits towards your physics major for them, for instance. Ian says, do you know the person or group who's working on quarks and or nuclear physics? So the quarks group is being led by Marina Artuzo, and she's actually in CERN right now because they're in the process of actually installing their new detector in the ring, which is the LHCb, the small ring, LHCb ring, because they look at beauty quarks. And so the B is for beauty. So she's actually in Europe right now. Part of the group is Matt Rudolph, Tomasz Skornicki, Steve Blesk. So that makes up the quark group. And then the nuclear physics group is run by Paul Sauter. And he does a lot of his work down at Jefferson Laboratory, which is a big national laboratory in the South. And so he actually will send students down there to do work. Most of the people here build detectors. So you cannot make a measurement if you can't see the thing. And so most of the people on the particle physics side, even the gravitational wave side, they build the detectors. So for instance, for gravitational waves, we have experts who actually build the interferometer that makes the gravitational wave measurement. So, you know, it's really cool to get the data and be able to analyze it and stuff, but you can't get the data without the machine. So people here make the machines.
I feel like that's really unique also to Syracuse, especially the gravitational wave side. There are not very many people in the world who do that. It's really cool.
Exactly. Okay, so that will have to be it for new questions.
Thank you, students, for asking so many questions. I was telling our professors before this meeting, the group of high school students attending these virtual lectures this year has absolutely amazed me, and that goes for this group as well. I was shocked when all your correct answers were flowing in, and you asked such fantastic, thoughtful questions. So I really appreciate you being here and for participating. Also, can't go without thanking our professors who have real lives and real-time consuming jobs and are spending their evenings at home with all of us. So students, I know you will join me in thanking our professors for spending their time with us and being here to teach you some cool stuff and also to hopefully help you learn about Syracuse. So with that, I will close today's session. Again, thank you all for being here and for your participation. So thank you for being here, and we will see you next time.
Thanks so much for coming.